Professor Lecture Series held by the Department of Chemistry, Universitas Indonesia. My name is Bayu Ardiansah, and I will be moderating this lecture series. From UI Resolve program, several world-class professors from top universities are invited and will deliver their expertise to our academic community. Before continuing to the first lecture series in organic chemistry, Dr. Muhammad Ridwan, as the head of undergraduate program, Department of Chemistry, will give opening speech. To Dr. Muhammad Ridwan, now the time is yours.
Okay, thank you very much, Dr. Bayu. So maybe I would like to shorten the opening speech. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. The honorable guest, the professor today, Professor Zahir Judeh from Nanyang Technology National University, and for the moderator, Dr. Bayu Ardiansah from the organic chemistry field. So because usually the opening remark will be from Dr. Asep, but Dr. Asep have other schedules, so maybe I would like to represent Dr. Asep as a head of department. So first of all, I would like to thank you again for Professor Zahir Judeh for contributing to our program, this UI Resolve for World Professor Lecture Series. From Professor Zahir Judeh is expertise in organic chemistry from NTU, Nanyang Technological University from Singapore. So for all the participants, all the students, the research doing the students from doing research, and also organic synthetic chemistry class. So this is this is a rare case. I mean, for the world-class professor having a lecture here in the chemistry department. So I hope that you pay attention carefully with the lecture from Professor Zahir Judeh, and hopefully we can get the benefit from this one, from this lecture. And then this program also would like to increasing the academic and international academic atmosphere. So we invite the QS 100 QS professor, university professor, so to have a lecture in chemistry department. So this is the target of this program, UI Resolve. So without further ado, again, thank you very much for Professor Zahir Judeh for the contribution, and I will give back the time to Dr. Bayu. Thank you very much.
Thank you so much, Dr. Muhammad Ridwan, as the head of undergraduate program, Department of Chemistry, for opening this lecture series. And I will inform you again. This is UI Resolve program held by Department of Chemistry and fully supported by Universitas Indonesia. In this program, we have several lecture series. Lecture series in organic chemistry, lecture series in physical chemistry, and more lecture series. For lecture series in organic chemistry, we have 3 sessions, and this is the first section. Will be delivered by Professor Zahir Judeh with the title Cascade Conversion of Carbohydrates of pyrrole and indoles. Before the time I give to Professor Zahir, I will give the short biography of Associate Professor Zahir Judeh. He is graduated from University of New South Wales, Australia, and he joined National University Singapore as a postdoc fellowship, and then Astar as a senior research fellow before moving to Nanyang Technological University, Singapore in 2004. His research interests include organic synthesis, medicinal chemistry, and drug formulation. He has published over 90 peer-reviewed research journal articles, and he has consulted for several multinational companies such as Johnson & Johnson, ExxonMobil, Merck, and etc. With his excellent profile, this is our benefit to have Professor Zahir presentation in our community, in our class. So please pay attention to his presentation and make a note because the material of this presentation will be, inshallah, beneficial for everybody. So without further ado, the time I will give to Professor Zahir Judeh to present his lecture. So Professor Zahir, the time is yours now.
Thank you so much, Dr. Bayu. I would like to thank the head of the chemistry department, Dr. Asif, Professor Amina, Dr. Bayu, and of course, my good friend, Dr. Ridwan, for inviting me to give this presentation. So when we had discussion with Professor Ridwan and Professor Bayu about the presentation, the idea was to kind of give something that benefits the student. And we came up with the idea of talking about my research. And I chose a piece of research that really is very simple, but have very, very high impact. And it is the work of one PhD student who graduated just a month ago. So I am going to talk about her work for the past 4 years. I divided this work into 3 sections. So we are going to see the first section today. At the end of my presentation for the first section here, I have a question for the students to really kind of try to solve, because that will be the introduction for the next part of the presentation. I want to build on the knowledge of how do we take a small little piece of research and we expand it. So the idea here is not just to show the chemistry for the students, is also to understand how does research evolve from something that you do in the lab, a small thing that you kind of try, and then it evolves to kind of a big research area. So for us, initially, everything started from a small piece of work that we did, and it expanded for an entire PhD. And I'm looking for a second student to expand this area of research. I chose a simple topic today to show you, which is conversion of carbohydrates to pyrroles and indoles. We know that majority of the chemicals that we have at this stage are coming from non-renewable fossil fuels. This cannot continue on and on and on, because these type of fuels will kind of one day expire. And therefore, we have to have another source where we can produce things basically unlimited. Of course, carbohydrate is one of these things that come into mind, considering that 75% weight by weight of the plant biomass is made from carbohydrates, and carbohydrates is everywhere in this world. Of course, Indonesia is rich in plants, and therefore they have lots of carbohydrates. So these are really ideal materials for production of what we call a platform chemicals. So what are these platform chemicals? These are things that we can make maybe in 1 or 2 steps from carbohydrates. We call them platform chemicals. Later in the slide, I will show you more of these platform chemicals. It is a good research area because the research at this stage is really in its infancy, I would say. Not a lot of research has been really carried out in this area. If you look at my diagram here, what I'm showing you is I'm showing you basically different sources of carbohydrate and what does these sources produce for us, right? For example, we have potatoes that can produce starch for us. We have alginate, we have pectin, we have cellulose, we have chitin, chitosan that produce chitosan for us from the prawns and the crabs, the shell. So all of these materials are, a good source of carbohydrates. And as I said before, this is basically unlimited source of carbohydrates. I'm not sure why I'm not able to get my, sorry. I need to see if I am able to get my pointer. Sorry, it seems that my laptop doesn't want to show the pointer. I'm sorry. All right, we'll just have to continue like that. So because we are talking about carbohydrate, I thought for us, it's important to understand the classification of carbohydrates and really understand a little bit about examples of the carbohydrates. So carbohydrates are generally classified into monosaccharides and disaccharides and oligosaccharides. Of course, we have the polysaccharides. Okay, majority of the work these days to produce platform chemicals comes really from the monosaccharides and disaccharides. These are the major chemicals that we can get platform chemicals from. Oligosaccharides and polysaccharides are basically used a lot in the pharmaceutical industry, either as carriers for drugs or materials as excipients to produce drugs. So to produce platform chemicals, we focus on monosaccharides and disaccharides. Monosaccharides, we are talking about trioses, tetroses, pentoses, hexoses, and heptoses. And these are respectively 3, 4, 5, 6, and 7 carbon chain carbohydrates. They are basically classified into aldoses and ketoses. If you have an aldehyde group, it's called an aldose. If you have a ketonic group, it is called a ketoses. Disaccharides, we basically have 3 examples like maltose, lactose, and sucrose. So in here, we have 2 saccharides linked together. We have also the raffinose, steichose, and verbicosose as oligosaccharides. Let me show you some of the examples that I am going to use in my research to produce these indoles and pyrroles. Examples are shown to you in these slides, and all of these are actually aldoses because you can see the aldehyde groups over all these structures, right? All of them have these aldehyde groups. And you can see that I have 3 carbons, 4 carbons, 5 carbons, 6 carbons, all along these examples. It is important to understand that sometimes I have 5 carbons, but I have different carbohydrates. This is because of the arrangement of the OH groups, either to the right or the left. We also have ketoses, in which a keto group is present in these aldehydes, as you can see here, 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 and here. It is also important, if you are doing research in carbohydrate, to understand the enomer effect or the enomer phenomena. So if you look at this carbon here, I labeled as carbon number 1 here and here and here. You can actually move from a closed ring compound to an open chain kind of carbohydrates. This happens through a process called diatomerism, in which a closed cycle is going to an open chain, or an open chain is going to a closed cycle, especially if the carbohydrate is present in a solvent. You also can move from the alpha form, in which the OH group here at the anomeric carbon is pointing down, to the beta form, in which the OH group is pointing to the up. When doing research in carbohydrate, it is important to understand these two things, because once you are using a carbohydrate, you can get isomerism in which alpha moves to beta or beta moves to alpha, and sometimes you get tautomerism, and you have to understand how do you deal with these kind of mixtures of compounds. Of course, when we talk about fossil fuel and we talk about sustainability, there are really 12 green chemistry principles that we have to pay attention to. When we designed our research, we thought about these principles, and we thought, how do we follow these principles in order for our research to be classified as green research or sustainable research? I'm going to go through these principles because it's good to have a reminder with these principles. The first one is your objective when you are doing reaction is to decrease waste. And waste comes from either starting material, it comes from reagents, or it comes from solvents that you are using in these reactions. The second objective is to design methods to incorporate maximum of the starting material, so that this is preserving an atom economy. No wastage of any atom that is present in the starting material that you use to obtain the product. So objective here is whatever starting material you use, majority of the starting material should be incorporated into the products. Next, you have to design products that are having low toxicity or no toxicity at all. And then your product should have, your product should be designed with maximum efficiency in terms of reaction process. It is critical that you reduce the amount of auxiliary substances that you use in these processes. For example, the amount of protection to protection, the amount of reagents that you use, their mass. These are important things that we have to pay attention to. Another thing is the energy required for reaction. You have to control the temperature. It is best to do reactions at room temperature. Neither cooling is required, nor excessive heating is needed. Your reaction has to use renewable starting materials, such as carbohydrate, as we mentioned before. In your reaction, you should avoid protection and deprotection. Carbohydrate chemistry is notorious for its reactivity, because you have so many different OH groups, and the reactivity of these OH groups are very similar. They are very close. Therefore, protection and deprotection methodologies are used to avoid reaction of certain OH group, which becomes really a waste. Your objective is to use catalytic reactions, not stoichiometric ones. Therefore, the catalyst you use, it has to be a true catalyst with the possible minimum amount of the catalysts. And then your materials have to be biodegradable. The products have to be biodegradable, so their effect on nature is really very less. Another thing is that you have to develop a good analytical techniques, and then you have to make sure that your process is not prone to accidents. For example, we do not want to use explosive materials, starting materials, or reagents. So all of these things have to be kept in mind when we are doing these reactions. Now, considering all these principles and anticipating that we have really taken care to ensure that we stick to these principles, there are basically 3 processes by which you can use or convert carbohydrate to obtain platform chemicals. The processes that we use in the industry or in the lab, they are classified as thermochemical processes. So in this type of processes, a lot of energy is used. The other process we use is biocatalytic processes. And the third one is the chemical conversion processes. So every process has its pros and cons. Let's look at the thermochemical one. Its pros are as follows. It's a fast process. High energy is used here. In this process, we are able to access the platform chemicals, all right? But chemicals that are through hydrogenation and hydrogenolysis that cannot be accessed through biocatalysis are obtained here easily, all right? These thermochemical processes are really, really good to obtain fuels like alkanes and polyols. This is the most important application of thermochemical processes. The cons or disadvantages of using thermochemical processes is that these are processes really high energy intensive. You are talking about hundreds of degrees, 200, 300, 400, 500 degrees, right? And you have a limited choice of catalyst because of the extreme high temperature you are using. The catalyst cannot withstand, or many catalysts, chemical catalysts cannot withstand that much temperature. Therefore, this is a disadvantage, right? Their use in the synthesis of platform chemicals is very, very limited. As I said, these are really used to produce fuels like alkanes and polyols. Another disadvantage is that because heat is used, these chemicals, there is a requirement to use materials that have less than 10% water content in these starting materials. So if we are using carbohydrate as a thermochemical starting process for thermochemical reaction, then the water content has to be less than 10%. So you have to go through a drying process. Again, a drying process requires lots of energy to be used. Moving to biocatalytic process, this process usually is very mild. Yeah, usually these are done at room temperature or even at lower temperature, like -10, -15, right? In this case, because enzymes are very kind of selective, protection and the protection of carbohydrates is really not needed because of the good selectivity of carbohydrates. We can use a whole cell bacteria to do biocatalytic reactions. And some of the platform chemicals come from biocatalytic processes because they are very selective. The disadvantages for this is that we need high purity enzymes. In order to obtain high selectivity, your enzymes have to be highly pure as well as your starting material for the reaction. Because if your starting materials are not pure, your enzymes can be denatured and lots of side products are usually obtained. Usually, these have narrow operating conditions. Enzymes, they work. For example, bacteria, these are living things. They work on specific set of conditions. Any change in these conditions will change the entire process. They are very, very sensitive. Another thing is that we are producing here a high volume of wastewater. And that becomes a problem over the long run when you do this type of reaction for high batches. So you're generating a lot of waste and that you have to treat. Looking at the chemical conversion, the advantages for this is that this reaction, doing chemical reaction, you're able to change the temperature, solvent, the pressure easily. So our reaction tolerate a wide range of changes in temperature and solvent and pressure without much effect on the product itself. Of course, with these kind of changes, it means we are able to optimize the reaction, we are able to increase the selectivity and increase the yield. Here, because you are able to do this change easily, then you are able to optimize the catalyst very easily, systematically, to obtain high and multi-step reactions in this case can be obtained or can be done in one pot to reduce the cost of doing this type of chemistry. So you can, instead of doing reactions over 3-4 steps, everything can be done in one pot, in one flask, or in one container, and obtain your product. Here we are able to obtain the products that are not accessible in terms of, in the case of biocatalysis, because here we are able really to change the reaction conditions without affecting the catalyst much. Even our catalyst, systematically we can change. So we have a lot of room to develop and optimize. All right. The disadvantages are the following. Here, protection and the protection steps are really almost needed for every reaction, because chemical conversions are not as selective as biocatalytic reactions. In this case also, we are generating toxic reagents because we are using catalysts, because we are using purification like silica, we are using different types of solvents. Another issue here is the catalyst recyclability. Are you doing homogeneous reactions or heterogeneous reactions? All right. As far as our research is concerned, we have avoided the thermochemical processes. We also have avoided the biocatalytic processes, and we focused on chemical conversion. We know the advantages, and we also know the disadvantages. So in our work, we have completely avoided all of these disadvantages. Therefore, our reactions are done without protection, deprotection. So our carbohydrates that we use for reaction, we do not do protection steps or deprotection steps. Next, we do not use toxic reagents. All right. Yes, we do have some solvents for purification, but we avoid the use of toxic reagents. And our catalysts are really cheap, and these are things that you can recycle easily. We are using triethylamine, we're using acetic acid. These are the type of catalysts we use. So I hope that it is clear for our students to understand at the beginning of your work, it is critical that you understand how important to design your reaction to stick to the green chemistry and sustainability issues that you are trying to solve. Okay, as a result of this type of processes, which is thermochemical, biocatalytic, or chemical conversion, many products have been developed based on these processes. All of these products really start from C5 and C6 sugars. Majority of the sugar we use for chemical conversion or thermochemical conversion or biocatalytic conversion are either C5 or C6 monosugars. And from here, we have different platforms like the glycerol platform. This is our glycerol. We are able to obtain all these products based on a glycerol. You have the sorbitol platform, which is here. These products are obtained from sorbitol, right, as a starting material. We have the linoleic acid platform. Here's our linoleic acid, and all of these products are obtained directly or indirectly from the linoleic acid. We also have the hydroxybutyrylactone here, and all of these products are obtained from it. If you notice here that you have majority of the products here, they are actually simple chains, straight chains, or sometimes they can be branched chains. You have some example in which the product is cyclic structure, cyclic structure, cyclic structure. And what you also notice that is that there isn't really much cyclic structures that are aromatic, number one. Also, you notice that there isn't much structures that have heteroatom other than oxygen. Therefore, it becomes important to see if we can convert C5 and C6 into heterocyclic structures that has nitrogen as a heteroatom instead of oxygen. So I hope that our students are really able to understand what are we trying to develop here and how we designed our research based on what is available in the literature and what is really needed for industry. Coming back to the carbohydrates and to the issue of tautomerism, I wanted to highlight the presence of the aldehyde group here. If we are dealing with a cyclic hemiacetal, tautomerism gives us the aldehyde group. If we are dealing with ketosis, in which we have a ketal here, this tautomerizes to give us the ketone group. Our objective in this work is to use these type of structures to convert them mostly into pherols and furans. In the beginning, in our research, we have started our research with converting of these to furan, and then we moved to pherol. So in the beginning, we wanted to gain some experience with these reactions, and therefore we got furans as the starting research for us, and then we moved to pherol. So I will show you I will show you a slide about how we got the furans, and all of my talk will focus on pherols. So this slide actually summarizes all my lectures. And in this slide, here is what we are going to start with. We are going to take carbohydrates, pentosis hexoses, which is C5 and C6 carbons, and disaccharides. These disaccharides will have either C5 or C6 cyclic rings, and then combine them with active methylene compounds. When we do this type of reaction, we can obtain furans. When we combine this with different types of amines, as you can see here, we are able to obtain all of these different types of pherols. Now, our experience here obtaining these pherols led us to another kind of research. This research, instead of using carbohydrate, we use these hydroxyketone to obtain pherols. And there are reasons for why we use hydroxyketone. I will explain everything in the coming slides. And based on this research, we have moved to formation of these types of pherols. These types of pherols are really important because if you can do aromatization to this ring, you are able to obtain indoles. So you are able to obtain indoles from these pherols. I will explain to you how we got this. All right. So I will talk. The next slide, I'll show you our work of how we obtain furans, and then today I will talk to you about formation of these indoles. All right. So our work that we did to obtain furans is published in Green Chemistry. If you want more details, please go to this publication. But in short, we have carbohydrates reacting with malonitrile in water. Our catalyst is triethylamine. We are able to obtain these types of furans in more than 90% yield. All right. If you change malonitrile to malonamide nitrile, these are the type of pherols you are able to obtain. Right. We also can do a three-component reaction. You take the carbohydrate, you take this active methylene compound, and you take this amine, mix them together in presence of our catalyst triethylamine. You are able to obtain now these types of furan. These are 1,2-cyanoamines. These are amide amines, and these are already kind of, so this is primary and this is secondary amide amine. All of these have different uses in a pharmaceutical industry. So it's important to obtain these type of compounds so that you're able to form different type of rings here and here and here. All right. So going back to our story of making pherols, why did we wanted to make pherols? Of course, there is a sustainability issue, and there is good chemistry, simple chemistry that can give us good impact. But of course, whatever chemistry you want to use or you want to do, it has to have usefulness. This chemistry must be really useful for you or for somebody else. All right. Therefore, if you look at indoles, you will find that these are really widespread in different plants and microorganisms. There are hundreds of compounds that have been isolated, in which indole is part of their structure. If you look at the market, you will find that there are drugs that has indole as a core part of them. If you look at this drug here, alloracetam, it treats Alzheimer's disease. You have an indole ring here, part of the drug. If you look at Lipitor here, you have this indole as the core ring in this structure. As you guys know, this treat the condition. If people have high cholesterol, they take Lipitor, and this is one of the most highly sold drug in the market nowadays. It's a blockbuster, billions of dollar drug. If you look at this one here, this is our pyrrole ring here. This tolumetine, it is used to treat swelling for people who have arthritis and if their joints are kind of stiff and they have a swelling. This is an anti-cancer drug here. Pyrrole ring is shown to you here. And this is an antibacterial drug. This is our pyrrole ring here. This is an antibacterial, anti-inflammatory drug here. Again, there's another one here, another one here. These two here are potential drug candidates. This is NSAID drug, and this is an anti-tuberculosis drug that is being researched at this stage. It is also something to note that later in our work, we will make these drugs, this one and this one, as a demonstration of our research and how good is the research we have. All right. So if you want to do some research and you want to make indoles, the first thing you need to do is to really look for the literature and understand what is done in this area. So indole is not something new. We are not the first people to discover indole. This kind of compound has been discovered hundreds of years ago. So there are many different ways to obtain indole, and some of them are mentioned here. The older techniques are the NOR and Pol-NOR reactions, in which you have an aminoketone and an activated diketone in the presence of zinc acetic acid to obtain this indole, or you have a diketone and you have an external source of nitrogen to obtain these pyrroles. You have other methods as mentioned here, and all of these methods here have advantages and disadvantages. Sometimes these methods are a little bit complicated because you require to make starting materials before you actually make these ones. For example, here, this has to be made, right? You have to make this one in order to do this reaction. You have to make this one in order to do these reactions, right? So in short, there are advantages and disadvantages. Sometimes these materials produce a lot of toxic waste. Sometimes the catalysts are very kind of exotic, and sometimes you need higher temperature to do these reactions. Nevertheless, indoles are made easily in the literature. We are interested in these types of indoles, these types of pyrroles, because these pyrroles are really interesting compounds. They have contrasting kind of points. For example, this carbon here is electrophilic. The oxygens here are nucleophilic. All right. This section here, because you have OH groups, this is a hydrophilic section. This is an aromatic ring. This is a hydrophobic or a lipophilic kind of section, right? This is rigid. This is flexible. You have chirality along these chiral centers here because they come from the sugar. So there is a wide and different characteristic of this compound, which makes it an important intermediate. This is a very reactive compound. What I mean is that you can easily change this side or this side or on the nitrogen here. For example, here you can hydrolyze this to get the carboxylic acid. You can react at this side here to obtain a carboxylic acid at this side here. You can reduce this one to get the alcohol here. You can cyclize this to get this cyclic ring. And you can polymerize here, do a polymerization reaction. You can cleave this entirely and obtain an aldehyde, a formyl group. This is a very critical group for example, transformation to different products, especially chain lengthening. And you can actually entirely cleave this to get this kind of intermediates. So in the literature, these types of pyrrole are made as follows. You take an amino sugar, you take 1,3-diketone as an active methylene compound, sodium carbonate, and you react to obtain these pyrrole. You can obtain them easily, right? If you want to obtain a pyrrole that has a substituent here, what do? You take the amino sugar and derivatize the amino sugar, all right? And then do the similar reaction to get to this N-substituted pyrrole. However, these type of reactions are really having many disadvantages. First of all, the amino sugars are really very expensive, all right? And not all sugars have corresponding amino sugar. Therefore, the ring system is limited, all right? And in the literature, only 1,3-diketones have been used to react with amino sugar. Usually, low yields are obtained, all right? And sometimes a pre-derivatization step is needed to obtain these substituted N pyrroles. You have to have amino sugar converted to alkyl derivative of amino sugar. As I said, these are expensive material, and you can see from this slide that, you know, so for this amino sugar, glucosamine, the cost for 25 grams is 214. If I show you the price of the corresponding carbohydrate or sugar, you can obtain 1 kilo for $100. A huge difference in the price. I need 2,820 for 25 grams. Here, I only need less than $80 to obtain the same sugar. Therefore, if we are going to make an industrial process to obtain pyrroles from carbohydrates, definitely this is not a choice because of the price. This is very expensive. Yeah. So now our way of making this. So here is what the reaction is shown here. Yeah. So our way of obtaining, our way of thinking, how do we obtain this pyrrole is shown in this slide. Sorry. So I will show you what has been done in the literature. You take this amino sugar, 1,3-dicarbonyl compound, you obtain the pyrroles. Now, if you look at this, what you find is the following. This sugar, we can replace it, and we have unprotected sugar. And this nitrogen, it should come from an external source. This active methylene compound, it must be still there. So our thinking was the following. If we take carbohydrate, if we take a sugar, if we take an active methylene compound, and an external source of amine, we should be able to obtain pyrrole. That was our thought. This is our design. What type of amine sources we can use? We can use ammonia, ammonium acetate, or a primary amine, as you can see here. Of course, you can expand this to secondary amines, as we can see later. What type of active methylene compounds? Nitriles are really good materials to use as an active methylene compound. Examples are shown to us here. This is our active methylene compound. The R group here could be a nitrile, or could be this group here, or could be this group here. So this is the design that we have in our mind to obtain pyrroles. The next thing we did is, of course, we need to test our design, all right? And here is what I'm going to focus on. I'm going to focus on making this type of compound. So here is the test for our design. So we took sugar, we took the active methylene compound, this is a benzoyl acetonitrile, and we took this ammonium acetate. We mix everything together, and this is what happened. All right. We use the triethylamine as a catalyst initially. The reason why we use the triethylamine as a catalyst is because we had success in making our furanes. So it makes sense to use triethylamine again to obtain pyrroles. However, we also used acetic acid, all right? And we have also used different types of solvents to try and optimize the yield of the reaction. In case of furanes, our ideal condition was to use triethylamine, water at room temperature. That was our ideal condition. However, these conditions didn't work very well here. You can see that we are only able to obtain 45% yield of this product. Therefore, we have used DMF as a solvent for this reaction. The reason why water didn't work very well is because this does not dissolve in water, right? It's not water miscible. And this reaction took for ages to complete. If we want this reaction to complete, it really needs a lot of time, which is not really reasonable. Therefore, we had to change to another solvent in which everything we have, all our starting material are soluble and the reaction is homogeneous. DMF was the best out of the solvent we figured out. And this is the best condition that we have used. It gave us 96% of this pyrrole, unsubstituted pyrrole. Note that the reaction in the presence, if we don't have a catalyst, this reaction does not give us a product, all right? And if you do this reaction at room temperature, the yield is very, very low. So what became important is that temperature is important, solvent is very important, we want everything to be homogeneous, and we also want a reasonable temperature so that the reaction is completed at a reasonable time to give us the highest yield. Of course, we have tried different temperatures. Of course, we tried lower temperature, we have tried higher temperature. We noticed that if you use higher temperature, the reaction is completed in maybe 1 hour or 1.5 hours. However, the yield goes down because we have high decomposition products. Therefore, the optimum temperature is what you see here is 80 degrees. All right. So because this reaction is very successful, the next step we did is we wanted to understand, is this reaction general? Can we apply this reaction to different sugars? Can we apply these reactions to different nitriles? This is what we have to test. And this is called testing the scope of the reaction. All right. When you test the scope of reaction and you expand it, it is usually done at the best condition that you establish here when you do the screening of the reaction. So we took this condition and we screened different sugars. So the sugar we have used is are here. So we use ribose, and ribose was reacted with different nitriles. So no substitution, a methyl substitution, a methoxy substitution, a fluorine, and a bromine substituent here to see if the reaction proceeds and also to see the effect on the yield of the reaction. So we also did the reaction with xylose. All right, this is another carbohydrate. And again, we did it with the phenyl or with a methyl phenyl, as you can see here. This reaction also was done with galactose, as you can see here. And again, all what you see here is the following, that this reaction proceeded well with 5-membered rings, with 6-membered ring. It also proceeded irrespective of the chirality at the sugar. So the chirality doesn't have an effect. The number of carbons don't have an effect because the yields are always comparable and always high. So we can say that this reaction has a very good scope for converting sugars, pentoses, hexoses, with this nitrile to get the pherols. This reaction also worked with rhamnose. All right, rhamnose has a methyl group here, as you can see here, with our benzene ring here, a methyl substituent, bromo, fluoro, methoxy, and a chlorine at an ortho position, not just the para position. You can see that the reaction proceeds very well. It also reacted with glucose to give you similar products, and the yields are also really, really very good, more than 80% yield. Now, this reaction also proceeded very well if we are using disaccharides. We used maltose, all right? And this reaction proceeded really very well with different kind of nitrile to give you different pherols. Again, the yields are really good, over 82% yield. Not only with maltose, but the reaction proceeded with another disaccharide, silobiose, also another one, which is lactose. So this reaction, or the conclusion here, tells us that this reaction is general. It proceeds using different pentoses, different hexoses, different disaccharides, and the reaction proceed without loss of stereochemistry, without loss in the yield of the product. All right. Now, we also wanted to understand not just the effect of change of the sugar, we also wanted to understand if this reaction is general for other types of nitrile. Here we have benzoyl acetonitrile, and here we have oxo. We have the oxo-butanitrile here. As you can see here, the reaction proceeded well with different types of sugars. You have the ribose, you have the rhamnose, and you have the glucose. So these are 5- and 6-membered ring sugar, and the yields are really good. Okay. So this tells us that the reaction is really general. Before I move to the larger scale, what we notice here in all these types of reactions, we notice that when we wanted to purify these reactions, it was a little bit difficult to purify these reactions. What I mean by this is the following. These reactions are purified in such a way that we are taking the product of the reaction, and we are just only evaporating the solvent. When you do evaporation, vacuum evaporation, you are expected to evaporate DMF and triethylamine. But however, after some time evaporating under vacuum for some time, we found that triethylamine is still present, and we are not able to completely get rid of a triethylamine by evaporation. No matter how much you evaporate, no matter how much you keep it for vacuum drying, even 2-3 days under vacuum dry, NMR still shows that we have a triethylamine. All right. So the reason for this is the following. When you do this reaction, when you evaporate, you obtain a foam. All right. This foam here, triethylamine gets stuck to the product through hydrogen bonding. That's what we believe. So these compounds have a lot of hydrogen bonding, and triethylamine get incorporated into the structure of these compounds through hydrogen bonding. And that's why it's so difficult for triethylamine to be removed. Right. Let me move to this slide here. So one of the things that industry is looking for is if you are able to convert, or if you are able to obtain your product in large scale. Earlier, we are doing reactions in milligrams, right? Really very small, very small scale. Our objective was to see if the reaction is working and the yield. That's the objective. But so these reactions are done in milligrams. In order to demonstrate that our process is successful and can be scaled up, we have to scale up the reaction. All right. And we went from milligrams directly to 2-gram scale. Now, this is a big jump from milligrams to 2-gram. However, what we found is the following, that large-scale reaction works equally well as low-scale reaction. And if you take this ribose and react it with the benzoyl nitrile, you are able to get 86% yield of the expected pyrrole. Not only monosaccharide react in large scale, but also disaccharide react at large scale. So if you take maltose and react with this nitrile, you are able to obtain the expected pyrrole, as you can see here, without much loss in the yield. So the yield for large scale and the yield for small scale are comparable, indicating successful scaling up of the reaction. That's what this slide means. All right. As I said before, we are really interested in these compounds, and these compounds can easily be modified to other structures. So in this slide, I'm going to show you some of the modifications that we did for these types of compound. So we took ribose, we reacted ribose with the nitrile, and this is our pyrrole. All right. In this case, what we did, we cleaved out this section and we converted it to the aldehyde. All right, aldehyde. And then the aldehyde is reduced to this alcohol. This reaction is done in a kind of overall yield of 89%. When you're talking about this yield, overall yield for a few steps, this is really, really good process, a very good yield. So here we are able to convert our pyrrole to a formyl pyrrole and to a hydroxymethyl pyrrole, as you can see here. There are many reactions we can use to obtain, or we can convert aldehyde group to many other products. The other thing we did here is, it seems that these compounds have some kind of bioactivity, and we thought, can we make these compounds? That's why we tried this. So if you take this one and treat with Lewis acid, you will get cyclic structures here, and we are able to prove our structure by X-ray. As you can see here, this is our aromatic ring here, and this is our nitro group, nitrile group here. All right, this is our new ring that is formed. This is our oxygen here. Right. So this brings us to the chemistry of this section. All right. So the mechanism of this section. So Mechanism is something that we tried to work on, and we had a proof for this mechanism. Of course, it's very difficult to prove mechanism, but we have an evidence, I would say, for this proposed mechanism. So this mechanism is really simple. What we have here is our nitrile. Our nitrile react with our amine source, all right? And you get this intermediate, all right? By the way, this intermediate is stable. You can isolate it if you want to, all right? You can isolate this intermediate if you want to. Now, this intermediate reacts with our sugar. So this is our aldehyde group. Electrons are pushed here. These electrons come and react, nucleophile to electrophile, kick out electrons in the oxygen, and this is what we get here. All right? So this oxygen is this one here. The next step here is a base removes this proton. Electrons go here. All right? They make a double bond. Our double bond is here. And then these are kicked on the nitrogen to neutralize the positive charge. This neutron here. The next step here is a dehydration step. So loss of water gives us this double bond here. Now, the next step here is tautomerization. From the enol form, we move to the ketone form. So this is enol ketone tautomerism. And the next step here is this nucleophile react on the electrophilic carbon, kick out electrons in the oxygen, and this is what we get here. Of course, this structure is not yet aromatic, and it wants to be stable, therefore it wants to be aromatic. So we lose this proton here, electrons go here, this goes on the nitrogen, and the nitrogen pick up the proton to give us the pyrrole. All right? If you notice here that, so this has a molecular weight of 325. This is a 324, 306, 306, same, 288, plus the product has a mass of 288. This reaction, we followed the progress of this reaction using mass spectroscopy. Yep, using mass spectroscopy. And we took small amounts of the reaction mixture every half an hour, starting from 0.5 all the way to 3.5 hours. What we observe is the following, that we can observe the mass for intermediate 1, all right? We can observe the M+1 and M+2 for that intermediate. And for intermediate 2, which has the same mass, again, it's there. For intermediate 3 and 4, the mass is 306. We can observe 304. And for intermediate 4 and the product, we can obtain the 271, which is the mass minus OH, 289, M+1, and 290, M+2. Analysis of mass spectroscopy supports the reaction, the proposed reaction mechanism of this. All right, so here I'm just showing you that if you look at the product here, so initially we don't have any product here. If you look at that, so what we have here is this intermediate 325 and 308. 308 is here, 325 is here and here. All right, the value or the amount of product, which is at 271, increases. The amount of the intermediate decreases, increases here, more decrease of the intermediate, more decrease of the intermediate, and here at the end of the reaction, there are no intermediate products. Everything has been converted to the product itself. All right, so in summary, to summarize this, what we have done is we converted pentoses, hexoses, and disaccharides. These are unprotected sugars. We reacted them with active methylene compound or nitriles in the presence of an amine source to obtain pyrroles in 75 to 96% yield. All right, this is a one-pot reaction, 3-component, and triethylamine catalyzed reaction. The mechanism that we discussed before is a cascade mechanism that involves different name reactions like Knoevenagel condensation, oxo-Michael reaction, Thorpe-Ziegler-Taiwo reaction, and of course, ring opening induced aromatization. All right, this reaction is simple, as you can see. It's also very selective when the product is formed. All right, and it's metal-free. We don't use any metals as a catalyst for this reaction. We also demonstrated the reaction at a larger scale. 2 gram in a lab is considered a large scale, but I don't have any doubt that this reaction can really be converted or can be used in a very large scale. All right. Before I move to this one, so what I'm here for the students, I want you guys to think about based on the chemistry I taught you, how do you make this and this? How do you make structure 1 and structure 2? So this is what I want you guys to think about. But before we go for this little exercise, we need to go for questions. So does anybody have any question? I'll be very happy to answer.
Okay, thank you very much, Professor Zahir. Now, we in Indonesia is adhan for Asar prayer. So maybe please wait 1 or 2 minutes. Yes.
Okay.
Okay, thanks again for Professor Zahir for delivering the material. So students and participants, if you have any questions, please discuss with Professor directly. So this is the golden opportunity because usually for the synthetic organic chemistry class, we discuss, you discuss with me. Yeah, but here we have a prominent professor from World Class University. So please ask the questions.
I'll be very happy to answer any question. And of course, you can ask me questions, and I also have to ask you questions. So I got you 2 compounds for you to try and, based on the chemistry that I taught you, to try and make them, prepare them. But let's first answer any question that you guys have.
Okay, so before Prof. Zahir asks you questions, so you you ask him questions.
Yeah, I hope you will not ask me how to make the compounds. No, I will not answer that.
Okay. Raise your hand or just unmute directly. Okay. Still no discussion?
Seems that the students are shy today. Dr. Bayu, are the students in the class or everybody is somewhere?
For today's meeting, everybody in somewhere, not in class.
All right.
Yeah, but for the next the second meeting, it will be a hybrid in our seminar room.
Okay.
Okay. Yeah, usually for the synthetic organic chemistry class, I give the structure or target molecule, and the student try to design the target molecule by retrosynthetic analysis,
Right.
2 step or 3 step. Okay. Now we have the questions. So please unmute.
Excuse me, am I the only one raising hand, or who is? Oh, just
Okay.
me.
Yes. Yeah.
Okay, thank you very much,
Yeah.
Mr.
Mention your name.
Good afternoon, Prof. Zahir. I am Muhammad Alif Abdullah. I want to ask a question regarding the carbohydrate feedstock for this reaction. In the early parts of the presentation, you mentioned that usually people use 5-carbon and 6-carbon carbohydrates. Is there any reason why primarily use 5-carbon or 6-carbon sugars? Is it because of the ease of conversion, because the target compound that we want to synthesize is a 5-ring member, or is that any other reason? For example, if I were to use an 8-carbon sugar, would the reaction still work, or will there be other challenges? That is all from me. Thank you very much.
Thank you so much, Muhammad. Thank you. So the reason for 5 and 6, there are multiple reasons. The first one is availability. Yep. Availability of the 5 and 6 is huge in comparison to 7 and or lower. So availability is a critical issue. The reaction that we have mentioned, it applies to 5 to 6 to 7 to 8. We don't have a problem. However, this reaction, when we tried to use 3-carbon, it became a little bit sluggish, and we have multitude number of products. So for 3-carbon, we have work to do on it. The reaction is a bit sluggish. Multiple products are formed, but I think once we are going for 5 and 6 and 7, I think that's really basically this is what we need. So to go back to your question, availability is critical. 5 and 6 are very, very available, number one. And number two, majority of the product that industry need is basically compounds that have 5 or 6 carbons. And you are able to obtain, from these compounds, you are able to obtain 5 rings and 6 rings. So if you look at the intermediates for pharmaceutical industry, you will find majority of these drugs, they either have 5 rings or 6 rings, majority. We cannot use 7, or we cannot use 8 or 9 or 10 or more, because it becomes really complex. And if you use complicated carbohydrates, these reactions will not really work. Yeah, these reactions will not really work because the amount of aldehydes and ketones that are available is very, very less. Yeah, so we stick to monosugars, 5 and 6. We stick to 2 sugars. Yeah, either monosaccharides or disaccharides. Any other question?
Okay, Muhammad Alif, you got
Thank you
it?
for the explanation, Prof. Zahir. So if I were to summarize the answer, so the answer is it's not a problem of possibility of synthesis, but a problem of supply and demand from the carbohydrate and also the industry needs. So the industry wants the 6 carbon and 5 carbon rings. Is that correct?
That's correct. That's really correct. Yes.
Okay. Thank you very much, Prof. Zahir.
Thank you, Muhammad. Thank you.
Okay, we welcome the next questions. If you have curiosity, okay, from synthetic organic chemistry class, we call SKO, SKOB,
nice.
yeah, SKO. Please.
Good afternoon, Professor. My name is Fatul Hoyer from the Organic Synthesis class. I'm interested in the, if I'm not wrong, it's the proposed mechanism slides. So my question is, does the proposed mechanism is based on the purely theoretical point of view, or does the proposed mechanism is already is combining the theoretical point of view of synthesis and then like optimizing it based on real life experimentation, or does it comes from like any other source? Thank you.
Thank you so much, Fathul. Thank you. So the mechanism is really based on mass spectroscopy experiments. So what we did, as I said, we did the reaction in a flask, and then we took small sample and inject in the mass spectrometer. Every half an hour, we take a small sample and we inject, we take and inject. And then we record the mass spectroscopy. And after we record, we look at all of these spectra and we look at what are the intermediates and what are the products. Of course, this you have a number of peaks here, but if you look at the mechanism, you can really tie it away with the experiment we did. All right. Again, mechanism is a mechanism. There is no 100% proved mechanism, right? So here is proposed mechanism. And the proposed mechanism is really based on the experiment from the mass spectroscopy, number one. And also, it is based on this initial compound we obtain here. As I said, the reaction between these two starting material gives us this nitrile. And this nitrile is something that you can isolate and you can characterize. And it is available in the literature. So what we did, we took these two, we reacted them, we are able to characterize this. The next logical thing is that this, based on our experience, based on the literature, based on the logic, this reacts to give with the ketone, with the aldehyde, to give us the products. And so this is how we take this type of mechanism. So it is both theoretical as well as experimental.
Okay, thank you, Professor, for the answers.
Thank you, Fathul. Thank you.
Yeah, so the reaction mechanism is based on the experiment about the electron pushing and attacking the positive carbon an electrophile nucleophile is based on the nature of the atom, but the phenomena we get from the experimental result, especially mass spectrometry or NMR analysis. Okay, the next, we welcome the next question, if any, from organic class students or other students. Maybe from research students. Especially biochemistry or organic research group. Or from SKOA, organic chemistry class A. So I will not repeat this material again in the class. So please ask directly. Okay, Galen, please ask question.
Okay, thank you, Mr. Bayu and Mr. Zahir for the lectures and the opportunity. I would like to ask about the slide that summarizes your lecture today, in which you used the hydroxyketone to produce target molecule 5. My question is that, will the reaction be possibly done? Can the reaction be possibly done in case we use a derivative of benzoic acid instead of hydroxyketone? And what is the supposed, what are the approximations of the yields of those two reagents if it were to be done? I hope my question can be understood. Thank you.
Thank you so much, Galen. Thank you. So you are talking about this one here, right?
That is correct.
Right. So you are saying that, can we use carboxylic acid instead of hydroxyketone to do the reaction? Is that the question?
That is correct, Prof.
Yeah. So carboxylic acids will not work in this way. Reason is, based on our mechanism of the reaction, you need to have a hydroxyketone. This arrangement of hydroxyketone is needed, or at least hydroxyaldehyde. With carboxylic acids, you don't have the ketone group, you don't have the aldehyde group. The whole chemistry is based on the presence of a keto group and an aldehyde group. Of course, you have to have a hydroxy. So this arrangement is really important. And if you followed my mechanism, you will understand why a hydroxyketone is needed. I hope I am clear. And so if you have time, please also see the last lecture. I will actually talk about the mechanism of the reaction of formation of the indole using this. So please stay tuned for that.
Okay, Professor, thank you for your answer.
Thank you, Galen.
Okay. Do you have any other questions about the presentation material today? Very interesting about the synthesis of pyrrole and indole derivative from sugar, yeah, glucose or ribose.
Does anybody have any Any question? I'll be so happy to answer any questions that you guys have. I have a question. Is the process of development of the research clear to you guys? So when we are doing research, there's always like a smaller train going from this station to this station to this station. So is our research, how we developed this process, is it clear to you? From the concept, why did we do it? How did we take it? How did we do the screening? And then we check the scope and we check the mechanism and we did large scale. I hope this is really clear for those of you who are doing research.
And do you have any comment, students? Yeah, for me, this is really synthetic organic chemistry. Yes. So we, in my doctoral study, I also developed a synthetic method. And first, I use only one example.
Yep.
And examine the reaction condition. For
Yes.
example, the variation of temperature, variation of solvents, screening of maybe additive material or catalyst.
Yep.
Until until we get the best condition. Yeah. So
absolutely.
yeah, students can imagine that from only one trial. For example, in this slide, entry 1 using triethylamine and water as solvent. So before you run the reaction, so you must write down in your research notebook the reaction scheme that will happen, and then write how much milligram and how much milliliter you add each starting material and each chemical to the flask. You write down in your book, and then you start the reaction. After the reaction, your work is not done. So you have to purify. You have to perform column chromatography. During the reaction, you have to check by TLC, thin layer chromatography, and then after the purification, you check NMR. So to obtain the data for one trial is a long process. So you can imagine how long the organic research can be done. So this need very hard work, and then you need to deep thinking about what will you do about the organic research.
That is very true, Dr. Bayo. And I think also for the students, we have not shown you everything we have done in terms of screening. So this kind of table you see in front of you, it's called screening of the reaction conditions. So I have not shown you all the conditions. If I want to show you everything, you probably will have a table that is like 30, 40, 50 entries. All right. What I have shown you is something that is really a snapshot of what we have. So we have done reactions under different temperatures, different solvents, different times. This is important to do. We have done different bases. We have done different acids. All right. You have to cover yourself, because when you do this work and then you kind of send it for reviewers will ask you questions, many questions. Why haven't you done this? Why haven't you done that? Why? So you have to cover yourself. But then you stumble on a reaction and a condition in which is triethylamine 80 degrees, 4 hours, 96% yield. That is really good. However, all of you know that we are using DMF, right? Dimethylformamide. And DMF is not the ideal solvent for this. What is the ideal solvent? The ideal solvent for this is water. Yes, but the problem with water is that this nitrile does not dissolve and is not miscible with water. That is the problem. So the solution to this, what is the solution to this? The solution to this is two things. You can use a mixture of water and DMF. You can use maybe 80% water and 20% DMF. We have done this screening, and this screening didn't really give us better yield. The yield is almost like 45 to increase to 60%. So this is the logic of doing things. But then to avoid DMF, as I said, one way is to mix water with DMF. Another way is to use phase transfer catalysis. Phase transfer catalysis, so you have two solvents and you have your nitrile in one solvent and you have your glucose in water, and you want the phase transfer catalysis to happen in such a way that the catalyst will take the nitrile to the water and the reaction happens. But then we also examined phase transfer catalysis, and this reaction didn't give us better yields. So this is what we call research, and this is what Dr. Bayo was trying to explain to you. So we have a lot of screening. I've not shown you all the screening. I've shown you just what really a snapshot of that, and it just gives us the idea. But we have tried mixtures of solvents. We have tried other solvents. We have tried phase catalysis, phase transfer catalysis, and these things didn't really give us better yields. So we stick to DMF.
Yeah. Okay. Is there any question?
Go ahead. Does any of the students, undergraduate students, or even postgraduate, does anyone have a question about the process of research, the methodology of research, citing this presentation as an example? Does anybody have any question?
Okay. One person raise the hand. Please unmute.
Good afternoon, Prof. It's me again, Muhammad Alif. I have a question. So when you did the screening for the reactions, is there like a guideline or like this kind of overarching idea, or is it just a trial and error that guides through the research process? Because I'm currently doing my undergrad research myself, and although I have like a big idea of what my research process is, because it's a very novel field, bioinformatics, it's mostly trial and error. Is there any kind of like suggestions or guidelines in doing this kind of screening? Thank you very much, Prof.
So there is nothing called a trial and error. Yeah, we always need to have an idea. We have to lean to something. So for us to do this research, for you or for anybody to do a piece of research, first of all, you need to really understand the problem. What is the problem that you are trying to solve? For us, the problem here is very clear. The problem here is yield. Yeah, the problem here is low yield. Now, when we talk about low yield, then we need to understand, okay, how do we solve the problem of low yield? Okay, the problem here is compound 2 or the nitrile is not soluble in water. That is the problem. So the solution is, how do we make it soluble? So in your case, in your project, you need to identify what is the problem. So if you are identified what is the problem, then that problem will have a solution. All right. So there's no kind of a trial and error. Now, Where does the solution come from? The solution comes from the literature. People have done something. So in the literature, we know that DMF dissolve both the glucose and dissolve the nitrile. So if we know that, then DMF is a good solvent. We know that DMSO dissolve both. We know that methanol dissolve 5 and 2. All right, we know that. So you cannot have a solvent that doesn't dissolve 5 and dissolve 2. You have not solved the problem. So in other words, your understanding of the problem is the major contribution to the solution. And then once you understand the problem, proposing a solution becomes easy, and you have to depend on what is there in the literature. I hope I am clear. So if somebody doesn't know that DMF dissolve glucose and you go try so many solvents, you will just be wasting your time. That is called the trial and error. What is not a trial and error is the following. Your knowledge of a solvent that dissolves both compound 5 and 2, it is a must to have. So look in the literature, what are these solvents? For us, DMF is one of them. DMSO is another one of them. That's why we tried them. Am I clear, Muhammad?
Very clear, Prof. So, for example, if there's no literature, for example, regarding temperature, is there? This is just an example. So,
right.
Yeah,
right.
If there's no literature for some variable that we're trying to crack, what is the proper way of doing things?
Yes, very good, very good, very good question. So suppose, for example, I have no idea about what is the temperature that I should use. All right, I have no idea. Listen, in this case, what you do, you test 2 extreme temperature. You're not going to test every temperature. You must test extreme ones. What is extreme one? For example, the first thing I want to try is room temperature. And you know that we have tried room temperature, the last number 9, room temperature. This is the ideal one. So in our research, we go for ideal one. And why do we try room temperature? We tried room temperature is because sustainability issue, energy issue. And now we can see that there's nothing. So we go and try something. We don't try 10 degrees or 20 degrees or 30 degrees. No, we have to try something really high, 100 degrees, for example. Okay, so we have tried 100 degrees. And when we tried 100 degrees, we are able to obtain the product, but then there is a lot of decomposition of product. See, when you get decomposition of product, it means your temperature is high. For example, if you tried 100 degrees and you only obtain 30% yield and 70% unreacted product, it means your temperature is not high enough. So you have to increase the temperature so that the rest of the 70% is converted, everything. But at 100 degrees, if you have a lot of decomposition of product, it means your temperature is very high. Your starting material is decomposed, or your product is decomposed. So you go and lower the temperature. How much I lower? I go to 50, between room temperature and between 100. So in our case, we went to 50. And at 50 degrees, we still have some starting material, right? The comparison between, the compromise between 50 and 100, 80 was the optimal. So I hope you understand what I'm trying to say. So we go based on what our observation is. Of course, you will tell me that the temperature is a trial and error. Yes, I agree with you. And that's what we call research. Yeah. But fundamentally, it's not something that we pick up from air. So you will not go and do reactions at 200 degrees, definitely. Because you know that carbohydrates will decompose at that temperature. And you know that carbohydrates are not so stable at 100 degrees, right? For a long period of time. So you have to lower your temperature. That's what we call trial and error, but it's not completely trial and error. It is something that will have logic for it.
Okay, very comprehensive answer, Prof. Zahir. So for the students, especially research students, so please understand about the process. So this is not only on how you make your research, but also in writing your final project, scripts, thesis or dissertation. So you must understand about the problem and what literature did to solve the problem, what is missing, and what is your strategy to overcome the difficulty found in the literature. Okay. Maybe the next is go to your
Yes,
questions.
exactly. Yes. So you guys asked me many questions. Now it's my turn to ask you a question. All right. Okay. So the reason that I brought this question is I want you guys to. So if you guys have done this research, right? So this is the summary of my work, right? This just summarizes the work I did. So imagine that you are a research student or you are a professor who did this work. What is the next logical thing to do? Yeah. So this is called development, research development, research idea development. So that's why I brought this question. So considering what I explained to you, how can you make structure 1 and how can you make structure 2?
Good afternoon, Prof. My name's Akhdani Adli, and I will try to answer your questions. For number 1, for the reagents I used is aldopentose and oxabutanonitril, and for the amine source is propylammonium salt with the triethylamine catalyst. And for the number 2 is I use aldopentose and benzoyl acetonitril, and for the amine source is aniline salt with triethylamine catalyst. Is that correct, Prof?
All right. I'm not going to tell you if it is correct or not because I want to see other opinions. Akhandi,
Yes, Prof.
you have a very good and a sharp mind. Very good. Very good.
Thank you, Prof. Thank
Good.
you very
Very
much.
good. Very good. So I would like to have another opinion. If somebody has another opinion, I'll be happy to listen to that.
Okay, other students, please give the opinion, because this is one of the question I will ask in the midterm test also. So please try to solve this problem.
Does anybody want to contribute something? Dr. Bai, are we supposed to finish in like 7 minutes, or can we take a little bit more time?
Okay, it's up to you. It's up to you.
It's up to you. You are the boss.
Okay, maybe some one or some opinion
Yes.
more, and then we can discuss.
Okay. So I would like to hear another student.
we can keep one structure, and we just discuss
Right. Let's
one
focus.
questions.
Yeah, let's focus on structure one. Can somebody tell me how do you make structure one?
Hello, Prof. It's me again, Muhammad Alif.
Yes, Muhammad Arif, tell me please.
Actually, my opinion doesn't really differ from Adli's opinion. That's why I didn't open my mic. It's basically the same opinion. I'm just saying what he's already said. But yeah, judging by the structure, looking at the structure,
Yes.
This is just changing the R groups of the reagents,
Right.
but basically keeping the same sugar structure. So changing from phenyl to just a methyl, and then changing from hydrogen to propyl.
Okay, so you basically are saying the same thing, right?
Yes, I'm saying pretty much the same thing. Yeah.
I want somebody to give me a little bit different opinion.
Yeah, maybe one other student can propose.
All right, I can give you a hint. I can give you a hint. Maybe some of you can think. Think about your SN1 and SN2, specifically SN2 reactions. We are looking at structure one. So think about that. How would you use this reaction SN2 to obtain one? So, Dr. Bayo, can I choose one student?
Yeah, sure. With the SKOA. Please
Okay.
choose.
Oh, so SKOA, the first student I got is Nazila. Nazila is here.
Nazilha Khoirunisa.
Yes, that's right.
Okay.
If she is not here,
maybe it's here, but
yes, maybe Eric. So it seems that they are not here. They are here but not here. All right.
Yeah.
Okay, let me give you a clue. So based on the chemistry that I taught you, look, this is our material, yeah? So this is our starting material. Can I use this one as a starting material? So if I take this one as a starting material, and then I react this one with an alkyl halide, right? I take it and react it with alkyl halide. Maybe propyl bromide. So I will take this and I react it with propyl bromide, right? If I do this reaction, I will get my material here. Am I correct? Muhammad, am I correct?
Oh, yes, sir. Yeah, you can definitely do that. Yes.
Exactly. So that's what we can do, right? So, all right, Muhammad, can I do the same chemistry like what I just described here? I cannot, right? I cannot, right? So let me show you what I'm saying here. So this is going to be a slide for next presentation, and this is what we're going to talk about next presentation. So here, this is the reaction we have done here. You take carbohydrate, you take your nitrile, and you take ammonium, and then you obtain this product. A mixture of the carbohydrate, nitrile, ammonium acetate gives you the product. Now you can do alkylation reaction. You can use alkyl halide, and then this alkyl halide can give you the product that I asked you. All right. But the question is, I cannot obtain this type of compound from here. Therefore, we have to develop a new chemistry to obtain these compounds. And also, at the same time, if I am doing this step, this reaction here, to obtain this, this is a two-step reaction, right? This is a two-step reaction. The question we ask ourselves is, this is the question we ask ourselves, how can we obtain this one in one step? How can we obtain this one in one step? That is what, so this is the natural progression of research, all right? Because if you look in the literature, you will find that there are many compounds that has this kind of framework. The nitrogen is directly attached to aromatic ring, or the nitrogen is attached to an alkyl group. So your work that you have developed have to optimally obtain this one and optimally obtain this. All right. So this is what we call natural progression of our work. I hope this is clear. So in next presentation, I will talk to you about how did we obtain this. All right. Okay. I will not spend a lot of time and details on this work because this is the presentation I gave when I was at your university, when I visited Dr. Bai. But I will just present it for the student who have not attended. I will very quickly present this work, and then I will move to a different work. So hopefully the next presentation will cover these two topics, and the last presentation will cover these two topics. All right. But the reason, as I said, I just wanted you to understand, how did we progress our work? How did we move? What is the thought process? I wanted to not just share the chemistry with you, I wanted to share the development process, the thought process that we have. All right. Does anybody have any question?
Hey, anybody still have questions? Maybe some students leave the room because
Yeah. So no, please don't leave the room. Stay where you are. Yeah. So
don't be afraid.
No, please don't. So by the way, I always tell my students, before I give this presentation, I had another 2 hours presentation, 2 hours tutorial for my students. So I always tell the students, you please, especially, so this is advice for you guys. If you want to learn, it does not matter your answer is right or wrong.
Yes.
What matters is that you are contributing, you are really giving your opinion, what you understand. So professors don't look for right or wrong. Professors look for people who contribute so that they are able to explain more, find out where is your weakness and explain it more. So that's what we look for. I'm not here, I don't know you. Or I just gave a name. I don't know the person. I don't know any of you. So you can give me any answer. I'm okay. All I needed is just people who have who can contribute, and I'll be thankful for you guys if you just contribute and say what you think. I'm not looking for a right or wrong. Yeah.
Okay. Okay, maybe there is no question for this meeting.
Yes.
More. Okay, so maybe the question from Professor Zahir, you need to understand how the reaction process, how the reaction occur. For example, what starting material, what condition, and how the starting materials construct the target molecules. So you can determine what starting material 1 and what starting material 2. What is it's just like playing a puzzle. You try to draw. You try to find what are the starting materials. So please understand about the reaction scheme, and then from the question number 1 and question number 2 from the slide. So please try to draw the structure of the material needed to construct the molecular target. So several students try to answer, but please, especially for synthetic organic chemistry class, so write again in your book and determine what the starting materials needed to build the molecule. Then please study about the topic, because one of the question Professor Zahir asked to you, I will use the one question for the test in next 2 weeks. Just for information, Professor Zahir, the next 2 weeks in UI will have the midterm test. So this material is included to the synthetic organic chemistry topic. So I will use the material to the students.
I think Dr. Bayo has said something really important. So I wanted to, okay, if you guys look here, what do we have here? So we have a hydroxy group and we have a aldehyde group. Hydroxy, aldehyde, right? This is what we have. So when we did this work, right? When we did this work, so instead of using carbohydrate, we said we just need hydroxyketone or hydroxyaldehyde. This is hydroxyketone. But this hydroxyketone is on a, it's not cyclic structure, right? It's an open chain, yeah? So what we did the reaction with this one and we obtained the product. But if you guys look at this structure here, this is a dimer. This dimer contains hydroxyketone on a cyclic structure. Hydroxyketone on a cyclic structure. So this cyclic structure, this cycle here is here. I showed you in black. So if you do this kind of reaction, you obtain indoles, yeah? So what I'm trying to say is that understanding the basic principle of the reaction you are doing gives you a lot of room to develop and obtain different structures. And this is what I wanted to show in my research is how do you develop your research? We don't want to be static and keep always using carbohydrate, yes? So this is what we are trying to show you.
I'm sorry, Mr. Bayu, I think you are still muted.
Okay. Okay. Thank you, Mr. Muhammad. Thank you again, Professor Zahir, for giving us the lecture today. Very important, very interesting. So, because of the time limitation, meeting, so hope the presentation will be beneficial for everyone. So thanks again, Professor Zahir, and thank you all lecturers and faculty staffs who attend this meeting, and also all students and participants for this meeting. Please stay tuned in the UI Resolve program, especially in the organic chemistry lecture series. The second lecture series, second meeting will be on the next Monday, 27th of March at 3 p.m. Yeah, 3 p.m. Western Indonesian time. So this is the end of the meeting today. So thank you very much for your kind contribution, attention, and Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Jazakallah khair. Thank you all. Thank you for listening. Thank you.
Thank you. Thank you very much, Professor.
Prof. Zahir sudah keluar ya Pak Bayu?
Sudah.
Alhamdulillah. Lancar Pak Bayu, terima kasih Pak Bayu.
Nah, terima kasih juga Pak Ridwan.
Oh, ada Bu Yuni, terima kasih Bu Yuni. Terima kasih juga. Ditunggu di acara sesi kedua dengan Prof. Zahir Judeh di pekan depan ya Pak Bayu ya.
Ya, di pekan depan jam 3